Everybody. So last class we talked about resistance, we talked about Ohm's law, and we have discussed that resistance, which depend on what we call dimensions, nature of materials, and the temperature. So we say that resistance is equal to rho L by A. So resistance is directly proportional to the length of wires and inversely proportional to the area of wires, and this is what we call as resistivity. And also we have done last class that the resistivity is one that is determined by a nature of materials and the temperature. And last class we derived that resistivity is equal to m E square m by tau, where n is number density of a free charge carrier, tau is the relaxation times, that is the average time between every collisions or successive collisions, and E is a charge of a free charge carriers, and m is a mass of it. This is what we have done last class. And last class I told you that the resistivity which remain same for a particular materials, or that is defined by nature of metals. However, this is also determined by this also depend on temperatures. So yesterday we said why the temperature factor is this. Tau is the temperature factors. Tau is a if a temperature is higher, then the time between a successive collision would be less. So therefore, resistivity. This is how resistivity depends on temperatures. Alright, so today we will discuss the temperature dependence of resistivities. And the different material exhibit a difference, right? So it is not that every material should depend on a temperature same, right? So different materials depend on temperature differently. Alright. And one more thing that we should understand is that for a short range of temperatures, for a very short range of temperatures, temperature dependent is linearly for some materials. Alright. So for a very short range of temperatures, some materials, alright, like this is how it depends. This is resistivity of temperature of metal at temperature T is given by, this is 1 plus alpha T minus T naught minus T. So this is what we have. Alright. So this is the equations. This is the equations which defines how resistivity depends on a temperature. And this is not true for all, right? This is for certain materials, and that too for a very short range of temperature. That too for a very short range of temperatures. And this is rho T is resistivity at temperature T. I say resistivity at temperature T. That is the final temperature. This is the resistivity at temperature T naught. Resistivity at temperature, that is initial temperatures, and alpha is the temperature coefficient of resistivities. Temperature coefficient of resistivity. Temperature coefficients of resistivities. And T naught is the initial temperature. This is initial temperature, and T is the final temperatures. This is the equations. This is the equation, right? And I told you just now that it is not for all the temperature. This is for a very short range of temperature. All right. So especially the metals such as the nichroms, which I have shown you here, nichroms, manganese, and constantins exhibit these properties. And then the special, right, the nichrome, manganese and a constant, these metals, they weakly depend on the temperature. Resistivity weakly dependent on temperatures. That means if I vary our temperatures, resistivity doesn't vary much. Alright, look at the here, right? I go on changing temperature from 200 Kelvin to 400 Kelvin. The change of temperature is so huge, right? I just change temperature from 200 to 400, then 600, then 800. So that means this shows that the temperature dependence of such a metal, that is the nichromes, manganese and constants, are normally, the resistivity weakly dependent on temperature. So this is, and moreover, look at here. I've drawn a graph from this, right? That means if a temperature is for lower temperatures, then the temperature dependent is not linearly. Alright, so therefore I have shown you just the temperature dependent where the temperature dependent is linearly, right? So this is so since these materials which the resistivity weakly dependent on temperature, so therefore these materials are normally used for making the wire bond standard resistance. All right, so you may come across the heater, right? They put a wire, and those wires are normally nichrome, manganese, and a constant wires. And this equation can be rewritten like this. All right, I just write in form of resistance. I can just write in form of resistance. This is true like this. So for resistance also, right? So that means if resistivity depend on temperatures, then resistance also depend on that is how resistivity depend on temperature is same that resistance, right? So if I say this is how resistivity depend on temperature, right? This is also same as for resistance. So this is what we have. And look at here, this equation tells that the equation is a linear equations. Alright, equation is linear equations, and alpha tells you what we call a temperature coefficients, and that is slope. This is how it dependent, right? Alright, whether it dependent, this tells you a slope, and slope tells you the stiffness. If it is highly dependent in stiffness is little high, right? And sigma that rho naught is y interception, right? So this equation is a linear equation, this equation is linear equation. So therefore the metals such as nichrome, manganese and constants, this is how temperature resistivity of metal depend on temperature, that is linearly. This is one such a materials. And then next I would like to have you is another metal like copper and semiconductors. Copper and semiconductors. So for this, to explain this, and this is temperature dependent is little higher, right? Look at here, right? So I studied from 0 Kelvin, right? 0 Kelvin, then 50 Kelvin, then 100 Kelvin, then 150 Kelvin. So temperature dependent, right? Of copper, the resistivity, right? Resistivity depend on temperature is not that. Not weakly, right? The temperature resistivity exponentially changes with temperature. Resistivity exponentially changes with temperature as far as copper is concerned, right? So look at here, copper, and for copper and semiconductors, I can use equation that I just now I have written. This is what we have. This is the equation that we have done last class. We derived last class. That this is m divided by n e square rho. This is the equations. This is the equations, and this equation tells that. Look at here. This equation tells that. This equation explains the two graph. This is for copper. This is for semiconductor or silicon, whatever, right? Semiconductors. And now look at here now. For copper, resistivity increases exponentially with temperature. temperatures. Alright, and this can be explained by using these equations. Look at here, this is constant. Why? Because for copper, this is going to be an electron, mass of electron, that is constant. And this is also a constant. This is also constant, that is charge of electrons. And now the two factors, right? Two important factors. Two factors that determine resistivity is number density. This is what we call as number density. This is what we call as number density, and relaxation times. And relaxation times. Look at here, right? So for copper, since copper is a good conductor, and N is huge. This N is huge. Huge number, huge in number, right? N is a huge number, right? Number of N is going to be a huge in a copper. And then look at here. Now look at here. As temperature increases, look at here. As temperature increases, they won't increase in N, but increase in N is very small. Alright, I just say increase in N is very less or very negligible. Increase in N's with increase in temperature is very, very negligible. However, what about tau? This is the temperature factors. This is the temperature factors. So when I increase the temperatures, then the time of collisions, alright, electrons start moving very fast and they start colliding with the atoms and ions. Alright, that means the time of collision, the change is very significant. Alright, change in the time of collisions or time between the collisions or time of relaxations. Relaxation time is very, very significant. So there's little increase in number density. However, so much change in the time of relaxations. So I would like to write here for copper, change is huge or a significant change, appreciable change, and this change is very, very little. Alright? Change is very, very less or negligible. Change is negligible. So therefore, now I would like to write for copper. So for copper, this is going to be proportional to 1 by tau. Alright, for copper. Alright, why? Because I just neglect the effect of N. Why? Because the change of N is going to be insignificant, very, very little. So now I say as temperature increases, and there is decrease in this. There is decrease in the time of relaxations. There is a significant decrease in the time of relaxations. Because of which, therefore, rho increases exponentially. Rho increases exponentially. Rho increases. That is how we explain this graph. This is how we explain this graph. So I'm going to repeat this. For copper, the change of N with temperature is insignificant. Alright. So therefore the change of temperatures increases or decreases the time of relaxations. Therefore 1 by tau is going to 1 by tau, that factor tau is going to decrease. So therefore resistivity is going to increase. Exponential increase in the resistivity. This is how we are going to explain. This is for copper. Now what about in case of a semiconductor? Again I'm going to write here same formula. N is squared. Again both two factors. Same, I just say this is one factor, this is another factor. Now, as far as the semiconductor is concerned, N is very little. Initially, N is very little. n is very less, very small number, and a detail you will study in chapter number 14, right? And then, now look at here, type of relaxations, alright, is, there is hardly collisions taking place. Why? Because there is no free electrons available, right? Now look at here, as I increase the temperatures, this number is going to increase. As temperature increases, so many free electrons are created. So many electrons that is found in the valence bands gets into a conduction band. That means so many free electrons are created. However, the number of free electrons still remain very small. Therefore, tau almost remains same. Alright, tau almost remains same. So in a sense, in case of semiconductors, increase in the n is significance. However, the change in a relaxation time is insignificance. Alright, even though number is going to increase so much. However, the time of relaxation time almost remains same. Why? Because even number increases, however, the number remains less. If a number remains less means then relaxation time almost remains same. That means this is just the opposite, right? As far as semiconductor is concerned, the change in the n with temperature is very significant. There is a significant change in the number with increase in the temperatures. However, there is insignificant change in the time of relaxations. Why? Because the number are less, still numbers are less. So therefore, I write here resistivity is proportional to what I write as n. So as temperature increases, then n is going to increase. Therefore, resistivity decreases. This is the reason, right? Therefore, resistivity decreases. So there is exponential decrease in the resistivity. There is an exponential decrease in the resistivity for semiconductor. There is an exponential increase in the resistivity for copper. So this is how this is again very important for examination, right? Alright, this is how the effect of temperature on resistivity. Alright, now I would like to do electrical energy and power. Alright, now I would like to do electrical energy and power. Now look at here. I have a resistor. Look at here. I have a wire. This is resistant R, and this is connected to a cell, whatever, right? And look at here. And this is A, this is B, wire A and B. This is what we call as wire A and B. I just say wire A and B. Wire AB. And having resistance what? Having resistance R. Having resistance, and there will be a current like this. Alright, current goes from A to B. Current flows from A to B. So we would say that A would be higher potential and B would be lower potential. So I say that at A potential would be, potential is V of A, and at B, at A, right? At A, I'll write here A. At B, potential is V of B. And what is the potential difference? Alright, so I say a potential difference between A and B, potential difference between A and B is what we call as V of A minus V of B, which we call as V, which is more than 0. Why? Because current goes from higher potential to lower potential. Alright. Now what I would like to tell you is, in time t, in time delta t, in time delta t, delta q amount of charge, delta q amount of charge flows from A to P. Alright. And I say that since I is current, then delta Q would be equal to I delta T. That's the simple, right? The why? Because I is equal to delta Q divided by T. This is the current, right? So now I would like to say what is potential energy at A and what is potential energy at B. So normally I say a potential energy is given by QV. Potential energy is normally given by QV, QA, which we have done last chapter, right? So now I say that what is potential energy at A? Alright. So potential energy at A is going to be delta Q V of A. Potential energy at B is going to be delta Q V of B. Alright. Now I say what is the potential energy difference? Alright. So now potential energy difference would be equal to final minus initials, final potential minus initial potential, and this is what is the final? Final is going to be this, right? Delta Q VB minus delta Q VA. Alright, VA is higher potential and VB is a lower potential. So therefore, I can write this Alright, so this is a change in potential, right? So I just say POT, pot, potential energy, change in potential energy, POT pot, minus V delta, this is Y minus, is VA minus VB is positive. Why? Because VA is greater than VB. So therefore VB minus VA is going to be a minus of VA. So this is what we. So this minus, right? This minus is very significant. Alright. This minus tells that there is a loss of potential energies. Loss of potential. This minus tells that negative implies loss of potential energy. Loss of potential energies. This minus tells about loss of potential energy. Alright, and that means again I rewrite. I substitute the value of delta Q. Delta Q is equal to IT. So therefore I V delta T. This is the loss of potential energy. Loss of potential energies. This is the loss. So the potential energy is going to decrease. So potential energy is going to decrease. Alright. That means the free electrons losing potential energy and start gaining what? Kinetic energy. Free charge carriers start losing potential energy. This much amount of potential energy is lost by a free charge carrier, and in a way this much amount of kinetic energy is gained by a free charge carrier. Alright, so therefore I just say because of loss of potential energy there is a gain in kinetic energy. So just the law of conservation energy, from law of conservation of energy, law of conservation of energy tells that loss of potential energy is equal to gain of kinetic energies. Gain in kinetic energies. Alright, gain in kinetic energy, right? So therefore what I can write is this kinetic energy is equal to, therefore this kinetic energy, gain in kinetic energy is equal to IV delta T. This is kinetic. So that means when I say there is a gain in kinetic energy, that free electrons start increasing. The velocity of a free electron start increasing. Let's suppose that there is no ions, the atoms are present, the free electrons are free, completely free, right? Then velocity of free electron keep on increasing. Velocity of a free electron keep on increasing. However, it is not so, right? However, in case in a metal, free electrons keeps on colliding, undergoing collisions with ions and atoms. And we have discussed last topic that even if you apply electric field in a conductors, or even if you apply a potential difference in a conductors, there is no gain in there is no accelerations. And what we find is, there is average velocity of net average velocity of a free charge carrier. So now the question is where that gain in kinetic energy has gone. Alright, so the answer is very simple. The gain in kinetic energy is change in a loss during a process of collisions. Alright, electron undergoing a collisions ceaselessly or throughout the times, and the gain in kinetic energy is changed into a heat while caused by virtue of collision. Alright, so look at here. This is the change in kinetic energy. However, there is no accelerations. Rather, free charge carrier, I just say free charge carriers moves with steady dip velocities. And then where the kinetic energy is gaining, now look at here, the gain in kinetic energy is, now gain in kinetic energy is lost in a form of heat. Look at here, so gain in kinetic energy is now lost in the form of heat. So heating take place. Gain in kinetic energy is now converted into heating. Alright, heating take place. Alright, so therefore free electron keeps moving with a steady dip velocity. Alright, so therefore this is what? Heating take place. So now what is the rate of heating take place? Alright, so now I say the rate of heating. I say the rate of heating is equal to rate of doing work. Alright, rate of heating is equal to rate of doing work. Alright, rate of heating is what we call as rate of doing work. So therefore I write here, I'm going to write here, so what is that rate of work? And that rate of work is going to be delta W divided by delta T. This is what we call as a power. is going to be I V delta T divided by delta T, cancel out, so the power is going to be VI. This is power. So that because of this power supply, electrons start moving with the deep velocities. Alright? Electrons start moving, I go on supplying this power, so that electron in a wire start moving with deep velocity. So this is what we call as a power. And this power is normally supplied by a power source, that is normally a cell or a battery. So this is what we call as power, right? Power. And electrical energy is going to be, this is electrical energy, right? This is electrical energy, alright? This is electrical energy. So more time, more electrical energy the loss, alright? Less time, less electrical energy loss. The rate of losing electrical energy is what we call as a power. This is what we call as electrical energy. And electrical energy appears in form of heat. Electrical energy change into heat. So this is electrical energy, and that change into a heat. So therefore heating take place. Now this is a power. The rate of electrical energy is what we call as a power. Rate of electrical energy is what we call as a power. Or rate of doing work is what we call as a power. Rate of heating is what we call as a power. Alright, so now I just say Ohm's law. Talking about Ohm's law. Ohm's law say that V is equal to IR. Alright, so power V is equal to so I square R. This is another form of power. So again I say P is equal to I square R. This is equation 1. This is equation 2. Now third equation, what is I? I is equal to V by R. Alright. So therefore power is going to be V square by R square. R and R are cancelled out. So the final power again, this is V square by R. Equation number 3. So these are the three different equations, three different form of power. All are one and the same, right? So this is one form. This in form of voltage and a current. This is in a form of current and a resistance. This voltage and a resistance. So this tells us about the power of electrical source. All right, and that is that can be figured out in form of voltage and current. All right, so now what I would like to do is normally we get power from powerhouse. All right, except that the power you get from a battery cells. Normally powerhouse send a power far from a town. So now we would like to say there will be a loss of power. There will be a loss of power, loss of electrical energy via transmissions. Alright. So now the question is how to minimize the power loss during a power transmissions. So look at here, if I say if R is the resistance of a wire, transmission wire, R is a resistance of a transmission wire, R is a resistance of a transmission wires, the wire, which we can't remove. And I is a current which we, I is a current which the power is sent out from a powerhouse. Then we say that this much power is going to lose during our transmissions. This much power is going to lose during our transmissions. Alright? I square R. This is the power loss of power during transmission. Now the point is how to minimize this. So if you could minimize this, then more power could reach the town, right? So this is the point. So from a powerhouse, we send a power P. We send a power P from powerhouse, and power P can be figured out in form of IVI. Power P can be figured out in the form of VI. So that is VI. V is the voltage. V is the voltage with which the power is sent out, and I is the current. I is the current. Okay. Now this is fixed. How much power you are going to send from a powerhouse is fixed. Alright. So voltage is also a fix. With what voltage you are going to send out, and then with what current you are going to send out. So therefore I figure out, so current can be written as P by V. What we can change is, I can change the voltage, I can change the current, but however P should remain same. Why? Because P is a power with which powerhouse sends out. Alright. Now having this, PC is equal to, instead of I am going to put V, P square divided by V square R. Yes, this equation is very interesting equations. So this is a fix, and this is a fix unless I change a wire. We can't afford to change wire. Alright. And this I have a controls. I can control this. How I can control this? Look at here. Look at here. If I increase V, and PC is going to decrease. This is, look at here. PC is 1 by V square. If I increase V, PC is going to decrease. And if I increase V, and then I has to decrease. Why? Because P is constant. P is constant. Why? Just now I told you the power which I am going to send from powerhouse is fixed. So I can change the V. If I change the V, simultaneously I will change I. So if I increase a V, I has to decrease. Alright. So if I increase a V, then this is going to be less. This is how we minimize. Alright. I can minimize power loss by increasing a voltage and decreasing current. If we could increase the voltage by 10 times, then power loss could be decreased by 100 times. 100 times. Alright. So therefore, this is very important factors, right? Therefore, we can minimize power. We can minimize the power loss in transmission by sending a voltage, high voltage, and a very small current. This is how we would able to minimize power loss. So therefore, whenever you see a transmission wire, power transmission wire, you always see that very high voltage pole. That means this carries a power, and because of the fact that increasing the voltage, high voltage would decrease the power loss. So therefore, this is how we transmit. We send out power from powerhouse to a town, alright, such that voltage has to be very high and current has to be a very small. And then is it possible to use high voltage to us? No, right? And that part we will do next, maybe in chapter number 7, right? That is transformer, right? So this with this I'm going to stop, right? This is how to minimize power loss by increasing the voltage and decreasing the current. All right, and this is the final answer. Thank you.